All right, so more propagation frequencies. I mentioned transequatorial before. Look at the chart on that. Long path versus short path and more sporadic E. Ordinary and extraordinary waves, only because it's an exam question. Otherwise, I'm not sure you care. Ionospheric skip, chordal hop, which is kind of cool, but I don't know if there's any way to tell whether you're getting chordal hop or not. Some of the more or the sporadic E effects and ground wave propagation. Okay, so one of the questions before mentioned MUF, which is the maximum usable frequency. So it's the highest frequency that you can use to get a contact between 2 points via a hop. So the refraction in the ionosphere is a function of frequency and a function of angle. So you have to look at two of those things. But later we'll talk about critical angle, which is the highest angle that will still refract. And then also there's critical frequency, which is the highest frequency at a given angle where it refracts. The lowest usable frequency, or the LUF, okay, is the lowest frequency where it will refract. So anywhere between the LUF and the MUF, you get refraction at any frequency between those two ranges. The higher the frequency or closer to the MUF, the less loss, and you're going to have a longer hop. So what does MUF stand for? What's LUF stand for? I think it's out. Oh, you didn't like dog? Okay, that's perfect. Okay.
You're using refraction
Instead of
where I
reflection,
would be using reflection. What's that difference?
because it's actually refracted, which means it's bent. Okay, it's not like hitting the surface of a mirror where it's reflected. Okay, it actually goes into that layer of the ionosphere and gets bent, just like the light coming through your glasses, because of the curvature and the fact that you've got an index of refraction there. You're changing the speed, actually bends the light.
The end result is the same though, right?
Yeah, you could project the two lines, and at a certain point you'd have the effect of a reflected point, but it's actually being bent or refracted.
Difference the senior call for astrophysics or college, whichever it was, but when you reflect a signal off of the hard surface, you invert the phase.
Yeah. Yes. Yes.
Is there a way that you could measure that as to prove that the signal received is in the same phase as being transmitted, therefore proving refraction instead of inverted? Because at that point, it's a question of wavelength, how far away you are, and how do you detect?
You'd have to know the exact distance of the path.
Know that, so you can't really prove that it's out of phase versus in phase to call it refraction versus reflection. So
but
I see your point, but
it is true that electromagnetic waves, when they're reflected, like an antenna reflector, okay, is 180 degrees out of phase.
Right.
Just
You can prove that with filters.
Yeah, with light you kind of see, because again, we know exactly the distance.
well, but light is an electromagnetic wave.
Right. But we know the distances and we're not gonna be dealing with wavelengths to space a mirror and a sensor are exactly and so forth.
Right.
Yeah, yeah, but it'd just be tough to do it from an HF perspective. We don't know the precise distance to where it's reflecting. I mean, again, if you change your elevation of where it's refracting, you've changed the path length. And
Right.
therefore,
And that's why you want to refract off of the F2 layer. That's the highest layer, so you get the longest hop. Unless, of course, you're trying to get your neighbor, 50 miles away, and then then you're screwed. That's when you go to NIVIS.
You what?
That's when you go to NIVIS.
Vivid?
NIVIS,
Near vertical?
NVIS,
Oh.
near vertical incident refraction. And we'll talk about that again. So MUF is affected by the path distance and the location, the time of day and the season, and the amount of solar radiation and other ionospheric disturbances. So it's and there's things that tell you, I don't ever bother, but you can go online and find out what the current MUF and LUF is. So what factors affect the MUF? We get our first, all of above. So if the frequency is above the current MUF, it means it may be refracted, but it's still going to pass through the atmosphere. It's not going to be refracted enough that it makes it back down. If it's below the MUF and above the LUF, in other words, in between those two frequencies, the max and min, it's going to be bent back or refracted back to Earth. If it's below the LUF, okay, it just gets kind of refracted and this follows the layer and dissipates. If, and I'm not sure how that happens, but if the LUF is greater than the MUF, you can't communicate.
To me, that's like a square root. That goes to one. That absolutely makes sense, but I don't know how that. Yeah.
I don't know either. But if that happens, you probably have other issues besides the fact you can't communicate. How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF?
Charlie would be nice.
Yeah. Amplified. Okay. Alpha.
Charlie is probably a John Galt thing. What usually happens to radio waves with frequencies below the LUF? What happens to HF propagation when the LUF exceeds the MUF?
Gotta be out.
See, the only reason I brought that up is because it's a question on the test. Why you need to know that, I don't know. So frequencies that are just below the maximum frequency will have the lowest attenuation. And there's a lot of online stuff you can look up and tell you what the MUF is and what the LUF is. You can also listen for beacons on those higher frequencies that will give you an indication of what the propagation is between you and wherever that beacon is at that beacon frequency. And there's beacons at different frequencies all over the world that are always broadcasting. And there's sites where you can see those, I guess. I don't know if they show up on PSK Reporter, but some of those sites like that show beacons. Which frequency will have the least attenuation for long distance skip propagation? Which of the following is a way to determine current propagation on a desired band from your station? Oh, I like Charlie.
Yeah, Charlie's
Yeah.
the one, that's it.
Uh,
That much better.
oh, yeah. On the lower bands, the biggest problem is atmospheric noise. Like 40, 80, 160. And that's one of those cases where you don't care about gain. You care about being able to minimize the noise and have a very directional antenna, narrow bandwidth. And obviously, especially around here in the summertime, we have thunderstorms every day.
Somewhere.
Yeah, if you ever looked at what is it? There's a site that does a real-time map showing lightning strikes. Oh, I mean, there's little red dots here all the time. Which of the following is typical of the lower HF frequencies during the summer?
Photon absorption.
That's the one I like.
Yeah, that's a good one there.
Absorb light. But I'd have to go with the.
Okay. Transequatorial, we talked about that before, where you can go between two mid-latitude points that are the same distance north and south of the magnetic equator. It's slightly different than the geographical equator, although I don't think it's that big a difference. But it's my understanding they got to be in the 2,000 to 3,000 mile on either side of it. So it's kind of limited as to who can do that. Obviously not us. And it works in the afternoon or early evening. It's before the F layer kind of collapses into one. And the only chart I could find kind of showing this where you can have some refraction and it's managing to do a hop and just make it to the equator and then another hop. So you've got about 4,000 or 5,000 miles in between those 2 points. The other possibility is you can have this kind of defect or whatever in the ionosphere, because the ionosphere is not homogeneous. I mean, it's not a nice smooth layer up there, and it's got humps and bumps and things. So you could kind of hit one of those pockets, I guess you'd call it, and get a refraction in just one single hop from point A to point B. The effect's the same, it's just how it got there.
Yeah, but the second case, you're gonna have a higher signal reaching the receiver.
Right, because the first one you got lost when it hits the earth. So you obviously
have loss at both intersections.
Yeah, but you got one more loss
Yeah,
on the top.
Yeah.
So where is trans-equatorial propagation most likely to occur? I believe you're right.
terminate crosses propagation.
What's the approximate maximum range for signals using trans-equatorial propagation? If the last one was alpha, then this must be Charlie. At what time of day is trans-equatorial propagation most likely to occur?
Chuck.
A lot of Charlies. Short path and long path and both path. It's possible to have the signal go both ways and you can receive it, but with an echo or a, well, it's kind of an echo because one comes later than the other one. It's also possible to have a stronger signal on the long path than the short path. And that's what this one says. Sometimes the long path is better than the short path. The lower, well, basically the whole HF band supports long path propagation. 20 to 40 meters, I guess, are considered probably the best range. 20 is always in there is good for something. 40 would mean that you'd have to do it at night.
It's gonna be noise, so it's gonna be high,
Yeah. And 160, I guess, definitely in dark. So what's characteristic of skywave signals arriving at your location by both short path and long path propagation? Which of the following amateur bands is long path propagation most frequent? Which of the following is paths most likely to support long distance propagation on 160 meters? Sporadic E is usually when there's some dense patches of ionization in the E layer. And E layer is probably the most non-homogeneous of the layers. It doesn't seem to care since E layer is there 24/7. And I don't know that the E layer is affected that much during the day as opposed to night. Doesn't seem to be a big difference. But summertime is usually better for some of these sporadic E propagation modes. At what time of day is sporadic E propagation most likely to occur? At what time of year is sporadic E propagation most likely to occur?
Pretty soon. Yeah, true.
Ordinary and extraordinary. If you have a linear polarized wave and it enters the ionosphere, any of the layers, it gets split into what they call two independent waves. They call them ordinary and extraordinary. And they have slightly different propagation characteristics, meaning the refraction will be different between the ordinary and the extraordinary. So even though you got one signal going up, now I've got it split as it refracts. Plus, they're now rotating and they're elliptically polarized. Now, this is the only chart I could find that is for light. It doesn't exactly fit, except it is showing the incoming wave being split into the ordinary and extraordinary. But it's also showing a reflected wave because in this case of light where it's hitting that boundary layer between the two free space and the other medium, you get a reflection. It's hard to find much material on ordinary and extraordinary. I'm not sure why it's in here, but somebody decided it's a good question. So what are extraordinary and ordinary waves?
Repeating.
Yep. Okay, for maximum distance, okay, you want a low elevation angle because that gives you the longest hop. Because like a reflection, the refraction is going to come down at basically the same angle that it intersected the ionosphere at. Morning, Greg.
Yeah.
So the lower that elevation angle, the lower the incident angle. So the refracted angle is going to be a mirror of that. So you get the maximum distance. Particularly when you're doing it off of the F2 layer. And the higher frequencies that are below the muff are going to reach the upper part of the F2 layer, so they're going to get the maximum distance. So what effect does lowering a signal's transmitted elevation angle have on ionospheric HF skip propagation?
Chuck.
Chordal hop. This is kind of a special case where you can actually get kind of like a tunnel, except it's actually bouncing off of the F1 or F2 layer without going back to Earth. So you're getting multiple hops around because you got a low enough angle where when it refracts, it's going to come down and it's going to hit the ionosphere layer before it hits the Earth. So you're not getting those lossy hops off of the Earth. So this is kind of showing the upper part up here is normal hops going around like on a long path, a short path. Down here, you somehow, and I don't know how it actually happens. Maybe it takes one of those extraordinary waves, but your refraction is, like they're showing here, a different angle than the incident angle that it hit at. So it's enough that it's going to go down and refract off of the ionosphere several times before it gets back to Earth. They're showing it on the night side, probably because the F layer is collapsed into one and it's lower, which may account for the fact that the refraction is different. But like I said, I don't know how you would never know which way you were going. So what is chordal hop propagation? Greg?
Probably B.
What is the effect of chordal hop propagation?
I think that, great, sorry.
Why were you afraid?
Because I wasn't sure.
We won't make fun of you.
Well, you can't be right, if you don't speak up. Down in your own ear.
But I'm absolutely not wrong.
With great risk comes great reward.
Okay, we mentioned the gray line before. Unfortunately, it took the question out. So, yeah, I don't know why.
Cowboy,
Huh?
one thing that you can't cowboy.
Is the gray line question?
Well, gray line.
Oh, yeah. Well, they decided it wasn't important, I guess.
Wasn't deaf.
Then the picture that comes after, it wasn't, yeah, I think the way they couldn't prove it.
Say what?
It wasn't black and white, they couldn't prove it, so
Right.
that's a question. The gray area.
Okay, but supposedly along that terminator, you can get better propagation along between 2 points on the line.
If you watch any of the spotting pages that have a map like this on there, you can actually see it happen.
Yeah,
What you have to do to take advantage of it, I haven't quite figured out yet. But I can watch hops happening on there, by people spotting other people that they just spoke to.
yeah, it's a real thing.
So it works. Just have to figure it out yet, so.
Okay, ground waves are waves that travel parallel to the Earth's surface as opposed to going off at a takeoff angle and refracting, where these actually travel along the surface of the Earth. It's called a Norton surface wave. And it works well. The effect decreases with frequency. So the lower the frequency, the more of that effect you're going to see. It turns out, and it's not intuitive that it would be vertical polarization. I would have thought it was horizontal, but it's a vertical polarization. So broadcast stuff should do this, right?
Broadcast actually for FM is typically circular.
No, but I mean AM broadcast,
Oh, AM, yeah,
because they're all vertical. And I guess they do ground wave.
that's primary for local. For FM, well, I believe that it was aimed at, when most people used to put up an FM antenna in their house, they would use a dipole and string oil.
Yeah.
And a car radio antenna used to be vertical. So you take circular, you get 3 dB loss on either one, but you get both instead
All
of
right.
speed loss on both.
It's 3 dB loss of your polarization.
Yeah, it's just because if you're transmitting a vertical signal and somebody's got a horizontal dipole up, you're gonna lose that signal because they're opposite polarity. For most antennas, some broadcast stations on the FM band are vertical only. There are very few which are horizontal, I think, but most of them are circular.
What's in these little stubby antennas on modern cars?
Sharp fin.
The shark fin things,
Yeah.
well, I believe it's a patch antenna, like a,
Okay.
basically just a printed,
Because it works on AM too.
yeah.
I mean AM broadcast.
And GPS. there's, like
It's a
3 or
dual
4
antenna.
antennas in that thing.
Yeah, they'll have
Really?
multiple cables coming out, one for the GPS and or sat signal stuff, and then the second one for broadcast band. So it's an active antenna.
The camera uses the part, it's the grid and the rear to fog. It's not.
Oh, yeah, I had that when I was.
Oh, yeah, I've seen
Yeah, it was the old.
That's the,
Where I grew up in, had a little thing on the front window, not just the back, but it had
Yeah.
2 little lines, and
Yeah.
it went. up
Oh,
like
yeah.
this.
Yeah.
Oh, I remember that too,
Yeah.
But, so, yeah.
What type of polarization is supported by ground wave propagation? How does the maximum range of ground wave propagation change when the signal frequency is increased?
Sure. So,
Huh?
oh,
Just a comment I put
just
in
more explanation.
in case you forgot.
Forgot one.
So we talked about muff. Everybody knows what the muff and the luff is. And that when your luff's greater than your muff, you're in deep doo-doo. To find the best band, you can use, some of those internet reporting stations to see where the best propagation is and what frequency, what areas. Atmospheric noise is obviously worse in the summer on the lower bands, like it is now. It's probably 40 meters. It's probably 20, 30 dB higher than the noise floor now. Transequatorial, where you can go 2 to 3 thousand miles on either side of the equator and make contacts in the afternoon and early evening before the D layer goes away, I suspect. If you do short path and long path, you can actually get an echo if you're receiving it on both at the same time. And sometimes the long path is better than the short path. But again, I'm not sure how you know, other than they had some way to measure the delay. I guess.
The way should be constant for anything when you're hearing both, right? Because it doesn't matter where the other party is.
Well, the long path is always going to take
No, it's not.
farther. I mean, longer.
Depends on how far away they are.
Yeah.
Yeah.
If you
But
had a very directional antenna,
then you're not going to have
Yeah, not-
both directions.
well, you
No, but
could
you
measure
turn.
one.
And then turn it around?
Measure the other, or have 2 antennas.
Yeah. I don't
But
think anybody
then
does.
with RF, I don't think you can really believe that, because sometimes the long path will be a better signal than the short path.
Right. The only way you could tell is you could tell how much delay there is,
That-
but
That would be
unless
the
you-
way to tell.
yeah. I guess if you're talking to somebody and there's a much bigger delay, a noticeable delay in the response, but then how do you know that's not just them?
Maybe they just are thinking before they speak.
Yeah. Sporadic E, if you've got some dense patches in the E layer, a little bit on the ordinary and extraordinary waves. The main thing there is that it creates 2 different elliptically polarized waves. So I don't know how you tell which one of those you're actually receiving either. Chordal hop is kind of cool, but it's one of those I don't know how you know. And ground wave propagation, where vertically polarized waves travel along the surface for a longer distance than they would if they were just line of sight.
And don't they follow the curvature of the earth.
right.
That's why.
Somehow, I guess it's like well, I don't know. It's like there's drag on the wave or something on the surface that bends it, or just the difference in the density of the atmosphere between the surface of the earth and where the wave is. Could, if that is not a constant, then you could have a refraction curvature.